All right, what I want to do in this video is talk about Borel measurability of functions and particularly connect it to functions of bounded variation. And this kind of came up um, when someone asked, how do you do number 7 in our prelims, August 2017, number 7. And that is if you have two bounded variation functions, then prove that the composition is measurable. Right? So first of all, when you say measurable, you kind of need the, I guess for the prelims, it's usually Lebesgue measurability, but you really should say Lebesgue measurable. Um, but anyway, yeah. And so one thing I want to very quickly explain, because Royden only talks about bounded variation functions on a closed interval. So when we say a function is on a bounded variation on the real line, all we mean is that it's of bounded variation on each closed interval of the real line. There's no claim of uniformity for the total variation being finite or uniformity over all intervals, or rather, we take the supremum over all intervals of the total variation. That's not necessarily going to be finite. Particularly, we still want like the function f of x equals x to be of bounded variation. That's weird if it isn't. All right. But yeah, I'm not going to write it down. That's all we mean is that for each closed interval, um, rather, a function on the real line is of bounded variation if for each closed interval, the function is of bounded variation on that interval. Okay, so yeah, the cleanest way to do this problem, um, number 7, is probably through the concept of Borel measurability. There's probably other ways to do this. I'm not aware of them. I actually couldn't really find anyone giving a solution to this any other way. Um, so I'll be a little bit terse when I talk about this concept because it's very similar to Lebesgue measurability. The subtlety, the difference being the subtlety with Borel sets, being that what does it mean to be a Borel set? It just means that we're dealing with the smallest sigma algebra containing open sets. That's going to be crucial um, uh, to our discussion. But so let's say we have an interval. It could be the real line, it could be finite, it could be half open, half closed, doesn't matter. And you can make this definition a little more general, but typically you do this with respect to functions from a topological space to the real line, and I don't want to bother doing that, so no point. Uh, purposes. So a definition is a real valued function on I is Borel measurable on I. If the inverse image of each Borel set is Borel. So script B is a collection of all Borel subsets of the real line. And again, what does it mean to be Borel? It just means there's a smallest sigma algebra containing open sets. To remind you of that. Or the sigma algebra generated by open sets. Same thing. Smallest sigma algebra containing open sets. Okay, yeah. So, one of the nice things about this definition, this is a little bit different than kind of the way we formulated Lebesgue measurability in that with Lebesgue measurability, we wanted to look at open sets theta, particularly for a real value function. So remember, a function f on a measurable domain that spits out real numbers is Lebesgue measurable if and only if the inverse image of every open set is Lebesgue measurable. We want to be a lot more general on what sets we plot the inverse image for good reason. Really good reason is following. A little proposition, very, very, very easy. So let's say I prime intervals. And let's say f takes I prime real line. And let's say G takes I prime. And let's say these are both clear. Now, of course, here I'm thinking of this as a function from I to real line. All right, tensor composition. This is virtually trivial proof, but this is Borel. All right. What's let theta be Borel. Then well, not much proof. Take inverse image. So this is inverse image. Well, this is Borel because, well, this is Borel, assuming that. So that means because F is Borel measurable, that means this is Borel. Of course, domains match. So this Borel means the inverse image under G is Borel because, well, we're assuming G is Borel measurable. So F is Borel measurable. So this inverse image is Borel. G is Borel measurable. So this inverse image is Borel. So, and one thing I want to make clear is that if F is Borel measurable, then it's Lebesgue measurable. In particular, if theta is open, sorry, if F is real value defined on an interval and is Borel measurable, then it's Lebesgue measurable. And the reason is very simple. If theta is open, then it's Borel. So the inverse image being Borel means it is Lebesgue measurable. So the inverse image of every open set is Lebesgue measurable. And one thing I want to make clear too, I'll provide you with the page number and Royden Fitzpatrick in a second, but there are Borel measurable functions that are not Lebesgue measurable. And the interval here would be just 0 to 1. See, 1 second. Yeah, I don't think it's explicitly mentioned, but I think it's implicitly proved on page 53 of Royden Fitzpatrick. And again, what's that? basically, I'm gonna write it down. Yeah, there are Borel measurable functions that are not um, sorry, there are Lebesgue measurable functions that are not Borel measurable. So being Borel measurable is it's quite a bit stronger than Lebesgue measurable. Um, yeah. And I mean, we can even just throw that from the proposition because we've talked about this before. Um, Even on intervals, the composition of Lebesgue measurable functions is not necessarily measurable. Again, that's on like page 53 or the couple pages before that on Royd and Fitzpatrick. The section on the Cantor set and Cantor Lebesgue function. Um, okay, so next. So what's next is actually prelim problem, essentially a prelim problem. That's number one, August 2024. So even on the prelims, this concept is implicit, at least for the interval being realized. So basically what this problem is saying is if the inverse image of every open set is Borel, then F is Borel measurable. Borel measurable by our definition is the inverse image of B is Borel whenever B is Borel. Right? And I'll be quick with this because proof is very easy. And probably done in prior videos, maybe more than one video. So yeah, I'll make this. I'll write this as a proposition. We'll actually need this second. And it's an if and only statement. The converse is trivial. Not even worth writing, I don't think. So this satisfies inverse image of every open set is Borel. Theta is Borel measurable pi. If the converse is absolutely trivial, if F is Borel measurable and theta is open, then theta is Borel. It's a Borel set, and therefore the inverse image is Borel. So it's not very interesting. The constant. For this absolute standard, I won't go through all that detail. Basically, convenience, sigma algebra containing open sets, using the definition of Borel sets, and done. Or the definition of Borel set algebra. So let's say peak time is set of all theta, so it's a real line where the inverse image of theta is Borel. Um, you can check very easily that this is sigma algebra. And the reason this is some sigma algebra is because B is. It's easy self. If you are reading this and you're a UAlbany grad student going to take the prelim, I would expect the details, but yeah, we're almost done. But theta open implies the property we're saying is that this is Borel. And so by definition, that means theta is B. Okay, well, remember, B is the smallest sigma algebra containing open sets, and therefore it's contained in B prime. B prime is a sigma algebra containing open sets. Right. And again, I'll just remind you, this is the smallest sigma algebra, sigma containing open sets. And we're done. Because theta is in B implies theta is in B prime implies exactly what this is. Right. Okay, why is this important? Because of this really useful proposition, we can characterize Borel measurability in a way very similar to Lebesgue measurability. In a way it's much more useful for us to be able to prove things are Borel measurable. So this, as I said, is a very strong definition, because we don't know at all what Borel sets look like, and there's a lot of them, a ton of them, way more than there are open sets. Sigma algebra, small sigma algebra containing open sets. So F sigma sets are Borel, G delta sets are Borel, countable unions, countable intersections of these sets of Borel, complements of these countable intersections and countable unions, et cetera, et cetera. All right, and so I'll try to do this really quickly and not on here, but I don't know if I call it a theorem. And this is the proof. I'm not a very briefly outline it. It's very similar to the proof for Lebesgue measurable sets, Lebesgue measurable functions. On in section 3.1, page 54. So write down what theorem is. I is an interval, could be a real line, fine. So the following are equivalents to F being Borel measurable. So some more room. Second. One. As the usual, if you remember, the theorem proposition. It's a proposition in Royden even. So for NAC in a real line, the inverse image of C infinity is Borel. Open, same thing close, and same thing for the other kinds of C. Sorry, this is closed. We'll go about functions. Are included A, C, line, minus infinity to C is Borel, and very annoying, right? We don't really need it, but it's maybe good to know. Um, Further, um, each of these implies the inverse image of every singleton for C, remember, is characterizes Borel measurability. Uh, Check that, but it definitely Borel measurability, which is equivalent to 1 to 4, any of these 1 to 4s, applies the inverse image of each singleton. Didn't help me that much. Just more room for myself. But yeah, I'll outline the proof because it's very, very, very easy. Really nothing too new. Proof arguing exactly the same way as Royden, page section 3.1, page 54. Crazy here. And so we have I just sigma algebra properties. One's equivalent to 2. Is equivalent to 3 is equivalent to price there. Okay, so by 1 and 3, we have this is equivalent to F being Borel measurable. Why? Because in the image of an open set, this is going to be this, yeah. Uh, so remember, this is open. You can write this as say that we can write it as disjoint union. We don't care about joint of open. Okay, let's say it's open. We can write this union of open intervals. I guess will be this. So I mean the unit point. And this is for L because the inverse image of each this is particularly for every open interval, we trivial that 1 and 3 is the intersections, different C's, of course, 1A, 1B, A, B being my open interval. What if it gives you inverse image of every open interval is, and so that by proposition before that gives us that F is Borel measurable because the inverse image of open sets is Borel measurable. Any of or equivalent, if any of 1 through 4 are true, any being equivalent to all of them being true. Right. Last thing that we want to prove is trivial thing. So C is, of course, isophinity C, intersection C. So that means trivially follows. I don't really need this for what I'm going to do, but still useful. Yeah, so each one of these is Borel, so and that finishes. It's so yeah, why is this so useful? Again, it makes it much easier to prove concrete functions are Borel. So, for example, and it's kind of the whole point, and if remember things about in the previous video I mentioned Jordan's theorem. If not, I'll mention it. Really need to know the proof at all. Use it. Proof is pretty easy. Uh, so let's say F is monotone. Then F is Borel. Yeah, so you know Ron's theorem, you can kind of see maybe where this is going. Um, uh, okay, proof is very easy. Let's assume F is increasing, not necessarily strictly increasing, but it's increasing. Um, you can do decreasing proof almost the same. Assume F is let C be bigger than 0. So we potentially have two cases. Yes, trivial case. And you don't have to look at C infinity. You can look at any really 1 through 4, whatever. And you can look at closed too. Matter. So this is empty or equals so let's say it's either empty or singleton. That is not true, right? Both the empty set and singletons are Borel measurable. Right. So let's assume it's not empty. Let's assume it's not a singleton. So that in particular, it had at least two elements. So in this case, what we're going to do is not going to suddenly prove that we're going to use a very nice theorem from basic analysis, which is as follows. This is actually taken from Bartle and Sherbert Introduction to Real Analysis, fourth edition. Uh, Here, it's essentially the connectedness of intervals. So if S is a subset, real line that contains at least 2 points, and it has the property that x, y, and S with x less than y implies this whole interval between x and y is an S, then S is an interval. Very easy proof. But yeah, so we're going to use that. And the point is going to be that intervals are Borel, so the inverse of these is going to be Borel. Okay? No idea how you would prove directly that the inverse image of every Borel set is Borel if F is increasing. I don't think there is an easy way to do. I don't think there is a way to do it. But anyway, two just X, Y. Let's say this is S. Give it a name. That also generality. Let's say X is less than Y. Right. So I'm going to prove the closed interval X to Y is an S. If you, that's trivial, you can X to Y, um, then that means well, X is less than you implies it's increasing, so F seconds. I have brain fart there. So I'm gonna carry that line in that's not relevant, but um, uh right. So so yeah, I'll do it this way. F of U is able to define here. Because f of x is an s, the percentage of x given c implies u is an s implies arbitrary between x and y. Again, we exactly have this. That means S is an interval. Our case is that S, this inverse image, contains at least 2 points, has this property. Let's see for 1, 4. Implies S. And that implies we don't care that interval, we care is that this is Borel. Right. So yeah, the inverse image of C infinity is Borel, and that's that. Okay. Next thing is following so quick And this might appear in a future prelim just because it's literally the same proof as it is for Lebesgue measure. So it's just kind of making sure you understand that it's basically the same thing. Um, so it's basically a way of asking literal in a literal sense, we're not going to be asking the same question, but in a practical sense, we so the proposition is if f d take an interval r, be just realigning here. Um, both Borel measurable, then so is f plus d. Also, I'm going to prove it's trivial. Also, alpha f is Borel measurable, where alpha is just you could do this also for complex value functions. You just assume the real imaginary part are each separately Borel measurable. It's the definition. But yeah, again, I'll try to do this quickly. So you want to be bigger than. Uh, so you want basically you're looking at clear means, where do I next? These videos are always longer than I hoping. It's very quick, I guess. I mean, fill in details, things are never quick. So yeah, you know, same thing with for one of the measurable. This is equivalent to f of x is greater than q is greater than c minus qx. Uh, for some any count that subset of rational numbers. Oh, that means true if only if f of x is greater than q, and g of x is greater than c minus q. That's for some sigma. Yeah, so as usual, I'm just bringing g x over, bringing q over. Uh, yeah, so that means if you think about it, usual this equals union this inverse image. C minus Q. Basic properties. Well, and that's the proof. And again, the other part. Okay. Um, right. So now we can finally get to the solution to that prelim problem. Uh, yeah, and again, as I mentioned, it's this prelim problem number 7. I tried to find a cleaner way to do this or a different way to do this, and I don't even see it anywhere on the interwebs saying that. I guess I could, yeah, I'll ask ChatGPT to see if it can give me a different proof, but yeah, but it is a very clean proof. Uh, going through Borel. Okay. Solution to so yeah, uh, number 7, 817 numbers. Okay. So yeah, here. So yeah. So here, I and I prime are the real line. It's the real numbers. So I want to prove that each one of these is Borel measure. This proposition, uh, this proposition. So that is enough to show F, G, Borel. In particular, then the composition F and G will be Borel measurable. And that implies, as I mentioned, that implies Lebesgue measurability. Because the inverse image of every open set will be Borel measurable, and Borel measurable means Lebesgue measurable. So, so if F and G are individually Borel measurable, then the composition will be Borel measurable, and therefore will be Lebesgue. Um, Obviously, so you write this. So F measurable. If F is okay. So again, what does BV mean? I'll write this. It means it's bounded variation of every open every closed interval, and no claim that the supremum of the total variation on each of these intervals is finite, where the supremum is over all these intervals. All we want is F is bound variation on every A. Right? So for example, the function X is certainly bound variation on every A to B. Every uh, uh, monotone function is bound variation on every A to B. Every monotone function that's defined on the real line is a bounded variation on each interval. Okay. So we have to somehow use this, and what we're going to do is as follows. Kind of, I don't know if I'd say do the obvious thing. So do a very natural. I think it's really the only way to proceed. Um, so it's absolutely trivial that. So I want to show that each one of these is Uh, easiest way, the only way I know to do this is right as this union. Um, uh, where Fk is just basically F on Fk. That's a really good explain an easiest thing to do. And the point is that we know F is a variation on minus K to K. In other words, each Fk uh, and I don't want to even say on minus K to K because, well, this, each Fk is a function on minus K to K. Uh, so by Jordan's theorem, now, if you do the proof of Jordan's theorem, you need an endpoint to work with. So there is no Jordan's theorem for functions f that are bound to variation on the real necessarily. The proof makes no sense at all. And actually, that was an astute grad student pointed out to me, like, hey, Jordan's theorem, the proof makes no sense for these functions f and g. So how do we do this? So I was very happy. I was asked that question, though I actually didn't really have an answer. Um, this was yesterday. Anyway, so that means EFK can be written as I'll write it like this. FK1 minus FK2. And this is Jordan's theorem that each bounded variation function can be written as the difference of increasing. Well, that means increasing implies, as we proved, Borel measurable. All right, so we have a difference of Borel measurable functions, and that is Borel. So that means each of these percentages um, is Borel. Uh, Whereas the union, that means the inverse image and that's so once you get all these little propositions and stuff, all are very easy. Once we get these out of the way, proof problem is very quick, very clean, very slick. And if you have a different way to do it, let me know. If you know of a way to avoid doing this by just somehow directly or not there. I mean, another you need for Jordan's theorem on these FKs. But if you know how to do it without going through the concept of Borel measurable functions, let me know. But anyway. All right. Yeah, hopefully that was helpful. Yeah, that's a concept of measurability I use, I think, quite a bit in probability theory. I think it's actually maybe a little more useful than Lebesgue measurability in probability theory. But yeah. All right. Well, hopefully that helps. So long. Take care. Bye-bye. This is hopefully the last video I ever do. It's kind of a pain to make these videos, but I'm sure I'll find a concept or an idea that I thought I covered or I didn't, I thought I didn't need, but I do need, and therefore I need to make a video on. But anyway, maybe. All right, so long. Take care.